Up until now, we've been assuming that each of the independent variables has a direct impact on the dependent variable that's independent of the effect of other variables. In this video, we're going to talk about what happens when there's some degree of interaction among the variables. An interaction effect occurs if the marginal impact of one variable is going to be affected by the level of another variable. For example, suppose that you consider a production function where output is a function of labor and capital. The marginal product of labor, which is what the coefficient on labor in that function may represent, is going to be affected by the amount of capital the workers have to work with. Similarly, the marginal product of capital is going to be affected by how much labor is available to use that capital. So the impact of having more labor or capital will depend on how much of the other input is available. Another case where we might see this, and this is one of the first ones that was investigated by economists, is looking at the relationship between ability as measured by IQ and years of schooling on earnings. The basic notion here is that people who start school with a higher level of ability, as perhaps measured by IQ or some other type test score, may end up getting a larger return to an additional year of schooling. And if that's the case, the relationship between earnings and IQ and schooling is not simply a linear one. Instead, the impact of ability and schooling will have an effect that together may be greater than their separate effects. We normally represent interaction effects by adding an additional term to the regression to capture the combined effect of variables. In this case, we're assuming that the dependent variable y is in part a linear function of x and z as before, but now we're adding a new term to the regression, which is the product of x and z. With a little bit of algebra, we can show what the marginal impact of a change in x or a change in z will have on the dependent variable. And what we find is that the change in y over the change in x, the change in y that occurs when you change x by 1 unit, is equal to beta 1 as before, but now we have a new term there, which is beta 3 times z. So if we look at how y changes when x changes, there's a direct effect, which is that coefficient beta 1 as before. But now when x changes by 1 unit, there's also another term in that equation, which is beta 3 times z, which captures the indirect effect of x through z. So when x changes, it not only directly affects y, that effect will also vary depending on the level of z that occurs. Similarly, if we look at the impact of a 1 unit change in z on y, it consists of the direct effect as measured by beta 2, but it also includes this interaction effect between x and z. If we look at the first equation, a positive level for beta 3 tells us that when z is larger, a 1 unit change in x has a larger impact on y than it would with lower levels of z. Similarly, when beta 3 is positive, a 1 unit change in z will have a larger impact on y when the level of x is higher. A positive value for the coefficient on that interaction term tells us that the combined effect of two variables is greater than the sum of their separate direct effects. On the other hand, if beta 3 is negative, what that would tell you is that when one of the variables is higher, it would lower the marginal impact of the other variable. So a negative value of beta 3 would tell us that when x is larger, the marginal impact of z would be lower, and similarly, when z is larger, the marginal impact of a unit of x would be lower. So a positive coefficient beta 3 tells us there's a positive synergy or interaction between x and z. A negative coefficient would tell us that the combined effect is less than the sum of the separate effects of those variables directly.